All right, so I'm going to demonstrate how to run pplane for the particular example you were given in the notes, which was x prime is equal to x squared minus 4 times y. There we go. Finally, I'll get that. And then y prime is equal to x times y minus 4 times y. I suppose I'd note that p-plane is unique in that you don't always have to have the asterisk to indicate multiplication, but it reads this as x times y, and that's not common for computational codes and such. And I'm going to zoom in near, I guess, 0, 0. So minus 2 to 2, minus 2 to 2, graph the phase plane, and here we go. Now you just got through doing the linear phase plane, which was degenerate, but what you might notice is the trajectories actually tend towards 0, 0, as if it's a sink coming from this direction. But if I move a little bit too far to the right, say over here, now things come in towards 0, 0 and then tend to go off. And this is a very abnormal looking equilibrium point because it sort of is behaving. This is the analogy to the node in the one-dimensional case, where for some initial conditions you tend towards the equilibrium point, but for others you tend away from the equilibrium point. And there seems to be a break point where that changes. Just so you can kind of see what's going on, let me also show you the nullclines. Okay, so one of the nullclines is this parabola. And everywhere along this parabola, you see that the vectors are vertically oriented and headed downward. And the yellow nullcline is here, and they intersect at 0, 0, making 0, 0 an equilibrium point. But the local view is degenerate, and it disagrees slightly with the global. In other words, the local perspective, the local phase portrait, it was as if there was equilibrium point, equilibrium point, equilibrium point, equilibrium point, like infinitely many of them, and all the trajectories came in the fast direction, like this is indicating. And now that's that wasn't altogether wrong, but it's an incomplete picture because remember, the local view, the linearized view, does not include the nonlinear terms. And it's these nonlinear terms that are giving this nullcline the bend and are causing the true solutions not to hit infinitely many equilibrium points, but actually head towards the origin if you're on this direction, and if you're from this direction, comes in and then heads away from it. But the point is, there is only one equilibrium point, in fact, not infinitely many. And so this demonstrates why the linearized view slightly disagrees with the global view, because the global phase portrait includes the nonlinearities.